Good morning everyone, especially to our professor. Good morning sir. Now we will going to discuss mechanical compression refrigeration. Introduction. Mechanical refrigeration is a thermodynamic process of removing heat from a lower temperature heat source or substance and transferring it to a higher temperature heat sink. A refrigeration system is a combination of components and equipment connected in a sequential order to produce the refrigeration effect. The most common refrigeration system in use today involve the input of work from a compressor and uses the vapor compression cycle. This course is an overview of vapor compression refrigeration cycle. Principles of heat generation, transfer, and rejection. Mechanical refrigeration system. A refrigerant vapor is compressed by means of centrifugal, screw, or reciprocating compressor. Figure 2 to 37 is a schematic diagram of a mechanical refrigeration intake for a gas turbine. The psychometric chart included shows that refrigeration provides considerable cooling and is very well suited for hot humid climates. Mechanical refrigeration. Mechanical refrigeration is a simple process used widely in gas conditioning applications, hydrocarbon dew point controlling, but it is also used in NGL recovery application, NGL recovery application as the primary refrigeration option or in conjunction with another refrigeration option. How does a compression refrigeration system work? Vapor compression refrigeration systems are commonly used in industrial facilities to create environment and conducive to the preservation and safe storage of products. Next is the four main components used to create the refrigeration cycle. So first is the compressor. The cycle begins when the compressor compresses the refrigerant gas, raising the pressure and temperature. The second is condenser. The higher pressure gas then flows to the condenser where it releases heat to the surrounding or air or water, using it to cool and condense into a liquid. So third is expansion valve. The liquid refrigerant then passes through the expansion valve where its pressure drops, causing it to cool further and partially evaporate. So the last is evaporator. Finally, the cold refrigerant enters the evaporator where it absorbs heat from the area to be cold as it absorbs heat. It evaporates back into a gas, completing the cycle. The fluid undergoing the cycle called a refrigerant. Although theoretically the reverse Rankine cycle could be run with any fluid, only certain compounds and mixture are suitable for use in practical refrigeration. The criteria for the selection of refrigerants will be discussed later. The refrigeration capacity or QE of a mechanical refrigeration cycle is the rate of which heat is extracted from the surroundings at the step of evaporation. Energy balance for the evaporator gives QA equal M times H1 negative H4, where M equal rate of circulation of the refrigerant kilogram second negative 1. H1 or H2 etc is equal to specific enthalpy of the refrigerant at point 1 to 2 etc joules kilogram negative 1. The rate at which heat is rejected to the surroundings QA is obtained from the energy balance for the condenser. QC is equal to QC equal M times H3 negative H2. The theoretically mechanical power or watts supplied to the compressor is watt equal M times H2 negative H1. By virtue of the first law of thermodynamic process, thermodynamics for the entire cycle is QA plus QC negative watt equal 0. Next is the useful output. The useful of output of refrigeration machine is its refrigeration capacity. The cost of factor is the power input to the compressor. The energy efficiency of a refrigeration machine is therefore express it as its coefficient of performance or COP, dimensionless, defined as COP is equal to QA over watt equal H1 negative H4 is equal over H2 negative H1. Next is note COP is a thermodynamic concept different from the formal definition of efficiency of a heat engine. Therefore, COP can be and usually is considerably larger than 100%. Another practical expression of energy efficiency of a refrigeration machine is horsepower per ton of refrigeration. A real refrigeration cycle deviates from the theoretical cycle described above. The main reasons for division are: the compression is not adiabatic nor reversible. The power requirement of the compressor is higher than the theoretical value due to heat losses as well as volumetric and mechanical inefficiencies. There is a pressure drop due to friction along the refrigerant flow channels and not only in the expansion valve. The low pressure before entering the compressor or point 1 is usually slightly superheated to avoid wet compression. Presence of liquid droplet in the gas which may cause accelerate wear in the compressor. Despite thermal isolation, there is some heat transfer or losses of refrigeration to the refrigerant flow tubing between the expansion valve and the evaporator. And that's all. Thank you.